Hello students, today we see some examples on relation. So let us see first example. Let R be the set of all real numbers. Show that the usual order relation on R is a partial order relation. So here set is given us set of real numbers. So usually we denote set by A, but here set is denoted by R, and the relation defined is usual order relation. That means less than or equal to. If x is related to y, that means x is less than or equal to y. So this is our order relation. Now we have to see whether this relation is reflexive and symmetric and transitive. So since x is less than or equal to x for all x belongs to set of real numbers R. That means every real number is less than or equal to itself. Therefore, x is less than or equal to x. Therefore, xx belongs to R. Therefore, this less than or equal to or usual order relation is reflexive. Again, for symmetric or antisymmetric, if x is less than or equal to y and y is less than or equal to x, then we know that this happens only when x is equal to y. Therefore, xy belongs to the relation order relation and yx belongs to order relation implies that x is equal to y. Therefore, order relation is antisymmetric. Now, if x is less than or equal to y and y is less than or equal to z, then we know that x is also less than or equal to z. Therefore, xy belongs to the relation, given relation, and yz belongs to the relation, implies that xz also belongs to that relation. Therefore, this relation, order relation, is transitive relation. Therefore, since this relation is reflexive, antisymmetric, and transitive, we say that this relation is partial order relation. Next example, let R be relation on a set A. Then prove that R is symmetric if and only if R is equal to R inverse. That means we have to prove two parts or condition is sufficient and necessary. That means if we consider R is symmetric, then we have to prove that R is equal to R inverse. And converse part, if we consider R is equal to R inverse, then we have to prove that R is symmetric. So let us consider R is symmetric relation. So we have to prove that R is equal to R inverse. So if R is symmetric, then let pair xy belongs to relation R. If xy belongs to relation R, this implies that Yx belongs to relation R, because R is symmetric relation. This implies that xy belongs to R inverse. So this is implies and implied by. Xy belongs to R implies that Yx belongs to R, or Yx belongs to R implies that xy belongs to R. So this shows that pair xy belongs to R implies that pair xy also belongs to R inverse, and therefore this R is equal to R inverse. That means we can say that R is subset of R inverse, and by converse part we can say that R inverse is subset of R, therefore R is equal to R inverse. So now let us take converse part, that is, let R is equal to R inverse. Now we have to show that R is symmetric. For that, let xy pair belongs to R. This implies that xy pair belongs to R inverse because R is equal to R inverse. This implies that yx pair belongs to R. Thus, xy pair belongs to R implies that yx pair belongs to R. Therefore, R is symmetric. Thus, R is symmetric if and only if R is equal to R inverse. So, we stop here.